So we have the Hartman-Korpman theorem, which tells us that if we're looking in the vicinity of a hyperbolic fixed point, then the linearization tells us actually pretty much everything that's to be known about the vicinity of that fixed point. You just have the linear phase plane. You just stretch it and squish it, and then it turns into topologically the same thing as the nonlinear phase plane. So the question is now, what happens if the fixed point is not hyperbolic, meaning the linearization has some direction in which the eigenvalue has a zero real part? Okay, so let's look at that. Let's look for simplicity first in just a one-dimensional system. So let's imagine we have x dot equals f of x, and we allow ourselves a parameter mu that we change. And we assume that for the value mu naught, we actually have a fixed point x naught. So that would be a fixed point. And the question we have is, if we have this fixed point, as marked here, if we now were to change mu to another value from mu naught to mu, will there be another fixed point at that value mu? And will that be in the vicinity of that original fixed point? Okay, so we really want to do a local analysis, meaning we're imagining mu is close to that fixed point, and we're really, mu is close to the value mu naught. We're not looking for a fixed point that's maybe out in the boonies out there that may or may not exist and stuff. We're really only asking, will this fixed point, when we change mu, will it continue like this? So if we draw a line, we could maybe imagine, we could ask, will it sort of be like that as you change mu, the fixed point changes smoothly like that? Or will it suddenly disappear? Or maybe a new one appears. So that's the question. So since we are thinking about a local analysis, meaning mu is close to mu naught, and x is close to mu naught, so we say that explicitly. No, I don't want to have this. So mu is close to mu naught in magnitude. So this is small compared to 1. Then x minus x naught is also small. Well, in that case, we can use our good old friend, the Taylor series, and just expand f. So we use Taylor. And what do we get? We get, well, we're looking for fixed points. So we have that f of x and mu must be 0. And we expand around the fixed point that we have. So we have f of x naught, mu naught, plus stuff. Let's right away note that this thing here, this must be 0 because we have a fixed point. That's our basic starting point. Okay, expanding then around that, we get df by d mu times mu minus mu naught plus df by dx times x minus x naught plus higher order terms like second derivative with respect to x, x minus x naught squared, and so on. So since we're assuming everything is smooth, I mean, the function f is nice and smooth, and mu and x are close to the original points x naught and mu naught, that means these higher order terms can be ignored compared to these terms. And then we can simply solve for x, right? We want to solve for x in principle. And so now we can simply solve for it. So we get x minus x naught is equal to, f itself disappears because of the fixed point condition. We get minus df by d mu times mu minus mu naught divided by df by dx. Before we move on, I just should make sure that we keep in mind that these derivatives are all evaluated at that fixed point. I'm not going to write that down in the future, but we need to know that that is the condition at the fixed point, the derivative x the fixed point. And I guess I should keep here plus higher order terms, but they will not make a difference if mu is close to mu naught. And so we found a solution. So we can continue this branch, or we get a branch of solutions. Let's draw that. So as we change mu, we go through that fixed point, something like that. And there is a continuous branch. Which we could call capital X of mu, which goes through this fixed point that we started with. And this is the case if, we didn't say that yet, the important part is, this is the case if this term here is not zero. We need that df by dx at the fixed point from which we start must be non-zero. And so that's the statement of the implicit function theorem, that if you have a fixed point, and if df by dx is not zero, then there exists a branch, a continuous, actually a smooth branch of solutions x mu, such that x of mu naught is equal to x naught. So it goes through that point that we're talking about. And that continuous branch is actually also unique. That's also important to emphasize. So let me put that down here too. There's a unique continuous branch of solutions. Okay, very good. Before we ponder this a little bit further, let's just mention that you can do the same thing also in n dimensions. This is just more simple in one dimension. So let's just write it down if we have an n-dimensional system. So consider the situation that we have a differential equation x vector dot equals f of x and mu. And so x is not an n-dimensional vector, and f also. And then we do our Taylor expansion again of the fixed point. We assume we have a fixed point such that f of x naught and mu naught is equal to 0, which is a vector. Okay. And so if we expand, then we get again f of x naught mu naught plus, well, now we get the Jacobian of f. Let me call it L. L times x naught, x minus x naught plus df by d mu, mu minus mu naught. And then plus higher order terms, which I'm not going to start writing down, because we assume, now that the slightly different phrasing is, we now have to solve for x minus x naught. And so that we can do that if this matrix L, this Jacobian, is invertible. So the determinant of L has to be non-zero. So if it's the case, so let's write that down. If the determinant of L is not 0, then we can simply solve for x, and we get x minus x naught is equal to minus L inverse times df by d mu times mu minus mu naught plus higher order terms. And so it's an analogous statement. And so the implicit function theorem tells us that if the determinant of L is not 0, then we get a unique, smooth branch, also in n dimensions. Okay, so let's just say that once more, sort of more very concretely. So that means particularly that we have a branch. We have a branch. That means the fixed point persists as we change mu, and it's unique. No additional fixed points pop up. That's the key statement. Good. So there's one more thing to say. The question is now, how likely is it? Right? I mean, so we said if the determinant is not 0, then we can do that, then we get a branch. And so should we expect that to occur or not? And so one introduces the notion of generic properties. A generic property is a property of an equation, say, is a property that would be attained if you pick sort of random coefficients, if you don't have to tune a parameter. So if you imagine now you have this matrix L, the Jacobian, and so if you pick random elements, arbitrary elements in that Jacobian L, would you expect the determinant to be 0 or not? Obviously, in order to get it to 0, you would have to tune a parameter. And so you can say the determinant of L is generically not 0. Or in other words, generically, if you start at some fixed point, you will be able to continue it. It's only in special situations that you cannot do that. And those are the special situations we will be interested in, because if the branch just continues smoothly, well, there's not much happening on a qualitative level. Numbers change, but not qualitatively. Okay, so generically, we have a branch. And the other thing we want to point out is that we mentioned before that when the determinant of L is 0, that is when an eigenvalue of L is 0. But what is the L? Well, L was the linearization of our differential equation, right? So if we say x is equal to the fixed point plus some small delta x as a function of time, then we can expand around the fixed point and we get a differential equation for that small change, which will be L times delta x. And so the stability of that fixed point is determined by the eigenvalues of L. And so if the determinant is not 0, we get a branch. Or the other way around, we don't get a continuous branch. Things will happen if the determinant is 0. When the determinant is 0, that means an eigenvalue is 0. So as we change mu, what could happen is that the determinant is not 0, and at some point the determinant goes through 0. At that point, an eigenvalue changes sign, and at that point, the implicit function theorem doesn't hold, and means you can have a change in the number of solutions. And so the number of solutions can only change when an eigenvalue goes to 0, which means the stability of the fixed point you were talking about changes. So maybe we should write that down. The number of fixed points can only change if the stability of the fixed point in question changes. Okay, so as I said, the idea is, if I'm going to draw now a situation that's where the implicit function theorem doesn't apply, so say here, let me say here maybe the determinant of L is 0, it goes through 0, and then what could happen is that either this branch stops, or you could have more than one branch coming out. So that's something we need to now study, and well, we'll do that next time.